Welcome, everyone. Let's get started on mastering the heart of Apache Spark, distributed processing. Welcome, everyone. Today we are exploring the heart of Apache Spark, distributed processing. What exactly is Apache Spark? It is a unified analytics engine designed for large-scale data processing. Why do we need it? Because traditional, single-machine processing bottlenecks when data grows into terabytes or petabytes. By utilizing a distributed in-memory model, Spark keeps data in RAM and processes it in parallel across a cluster of computers, making it exponentially faster than legacy systems. Take a look at this diagram. On the left, we have a massive dataset that would choke a single computer. Spark breaks this data down into smaller, manageable chunks called partitions. These partitions are then sent across multiple worker nodes to be processed simultaneously. Instead of one processor doing all the work sequentially, you have multiple processors acting in parallel, drastically reducing the time it takes to get your results. Let us dig into the basics of how this processing is organized. Spark utilizes a highly efficient master worker architecture. The master is the driver program, which acts as the central brain of your application. It converts your code into a logical execution plan and schedules the necessary tasks. The cluster manager, such as YRN or Kubernetes, is responsible for allocating the necessary hardware resources. Finally, the worker nodes are the muscle of the operation. They spin up executors, which actually run the specific tasks and store the data locally in memory. In this flowchart, you can see the clear hierarchy of a Spark cluster. At the top sits the driver program, passing instructions down to the cluster manager. The cluster manager then communicates with multiple worker nodes based on available resources. Inside each worker node, executors are launched. These executors are where the real magic happens. They execute the individual tasks and keep data cached in memory for rapid access. It is a highly coordinated dance between orchestration and execution. Now, how does the data actually live within this distributed system? In Spark, data is divided into partitions, which serve as the fundamental units of parallelism. Whether you are using resilient distributed datasets or data frames, the data is immutable. This means that once a data frame is created, it cannot be modified directly. Instead, you transform it into a completely new data frame. By dividing the data this way, each CPU core in your cluster can independently work on a different partition of data simultaneously without worrying about data corruption. Looking at the visual, you can see a single data frame being logically split into 3 distinct partitions. Notice how each partition maps directly to a different CPU core on the right. This represents true parallel processing. Because the data is immutable, Spark does not have to worry about complex locking mechanisms or data overwrites. Each core independently processes its chunk of data safely and efficiently, which is the secret sauce behind Spark's incredible speed. Let us go a step deeper into the execution model itself. When you write Spark code, nothing happens immediately due to a concept called lazy evaluation. Transformations just build a logical plan. It is only when you call an action, like collect or write, that Spark springs into motion, generating a job. This job is translated into a directed acyclic graph, or DG, which maps out the most efficient physical execution plan. The DG scheduler divides the job into distinct stages, and those stages are broken down into individual tasks that run on the executors. This diagram maps the lifecycle of a Spark command. You start at the top by triggering an action. This creates a Spark job, which is handed over to the DG scheduler. The scheduler breaks the overall job down into logical stages. Think of a stage as a phase of work where data doesn't need to move across the network. Finally, the stages are split into tasks. A task is the exact, smallest unit of work that gets sent to an executor to process a single partition of data. To truly master distributed processing, you must understand data dependencies. First, we have narrow dependencies. This occurs when each partition of the child dataset depends on just one partition of the parent dataset. Think of operations like map or filter. Because the data does not need to be shared or sorted across the entire cluster to compute the result, Spark can pipeline these operations together. This means multiple transformations occur sequentially inside a single stage, processing them at lightning speed entirely in memory. Observe how clean and direct the flow is in this diagram. Parent partition 1 maps directly to child partition 1. The data stays strictly within its own lane. Because there is no cross-communication required between the partitions, there is absolutely no network overhead. Spark bundles these narrow transformations together inside a single stage, completing the computations extremely fast right where the data currently sits on the worker node. The counterpart to narrow dependencies are wide dependencies. This happens when the data required to compute a new partition resides in many different parent partitions. Operations like group by key or joins fall into this category. To perform these operations, Spark must reorganize the data across the entire cluster. This triggers a shuffle, which is an expensive process because it requires writing data to disk and transferring it over the network. A shuffle always marks the definitive boundary between one stage and the next. This diagram perfectly illustrates why wide dependencies are resource-heavy. Notice how partition 1 and partition 2 are sending data to multiple new partitions. The arrows cross each other, representing data physically traveling across the network between different machines. This is the shuffle. While shuffles are absolutely necessary for complex aggregations and joins, they consume significant network bandwidth and disk I/O. Our ultimate goal in Spark optimization is to minimize these shuffles. Let us apply all of this to a real-world use case. Imagine you are building a massive ETL data validation tool. Your requirement is to run over 2 billion data quality checks across 300 different massive datasets. If you tried this on a single machine, it would take days, or it would simply crash out of memory. In one real case, even the initial Spark job took over 4 hours. By analyzing the distributed query plans and addressing data skew error, one partition has millions of records, while another has only 2. The team was able to use the repartition command to balance the load, drastically reducing execution time. Here is the architectural flow for our use case. We start with 300 massive datasets. A very common pitfall in distributed systems is data skew, where tasks hang because one node has far too much data. By actively identifying this skew and applying techniques like repartitioning, we force an even distribution of data. Once the data is balanced, the parallel execution engine fires up, distributing those 2 billion checks across hundreds of executor cores seamlessly, resulting in a validated data lake in record time. To wrap up, optimizing distributed processing in Spark comes down to a few golden rules. First, size your partitions correctly. Aiming for 128 to 200 megabytes per task is generally optimal. Second, whenever you are joining a very large table with a small one, use a broadcast hash join to completely bypass the expensive network shuffle. Finally, always prefer the data frame API over raw RDDs, as this allows Spark's Catalyst Optimizer to automatically generate the most efficient physical execution plan. Thank you for watching. Please like, subscribe, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides. This final diagram shows the path to ultimate high performance. Write clean data frame code, let the Catalyst Optimizer create the optimal physical plan, and ensure you use right-sized partitions alongside broadcast joins. Your distributed architecture will absolutely fly. We hope you enjoyed this deeply educational tutorial. Remember to like this video, subscribe to our channel, and visit quicktechie.com for premium certification prep, including Q&A banks, full ebooks, audiobooks, full-length training, and interview guides.